Welcome.
Yeah, fantastic.
I am assuming our online folks are joining us now. That's fantastic. I want to thank people for joining us here in person as well. Good evening. My name is Joy Johnson, and it's my distinct pleasure to be the president of Simon Fraser University. And I want to begin in a good way by inviting Elder Marie of the Coquitlam Nation to come and provide an opening for all of us. So over to you, Elder Marie.
I raise my hands up to Creator ancestors, to all of you that are here today and online. Simon Fraser University respectfully acknowledges the unceded traditional territories of the Coast Salish people, including the Tsleil-Waututh, Coquitlam, Squamish, and Musqueam nations, on which SF Burnaby is located. I'd like to welcome Dr. Soo Kim and our President Joy Johnson. I heard maybe Mayor Hurley, is he here? I don't think so. Okay. Welcome visitors, guests, students, faculty, and staff to Empowering Agriculture and Food Security through 3D printing. This first event will feature Professor Soo Kim's research on technology and food security, potential role in reconciliation with Indigenous peoples, opportunity to explore food as a tool for reconciliation and resurgence. We need programs for healthy, equitable, and sustainable food systems. Indigenous Food Circle, which aim to reduce food insecurity, increase food self-determination. Some of these suggestions for continuing this work and the opportunity to experiment with food as a tool for reconciliation and resurgence. We believe that traditional knowledge, as well as addressing the social determinants of health, should be at the heart of food policies and practices of the government. Indigenous people in different areas have sustained themselves on the wildlife and plants that their areas produce. Various forms of agriculture have been practices by Indigenous people in order to sustain the soil and the lands. This knowledge has been used by Indigenous people, shared with their non-native brothers and sisters. Non-native brothers and sisters. The uses of plants and animals as medicines and foods were common among Indigenous people. Indigenous peoples have been removed from their lands, displaced their food systems, forced to assimilate into dominant settlers' colonial cultures. With installing fish hatcheries, for one, at our Coquitlam watershed, bringing back our salmon, we can go back to our fish diet. Bringing the rights to hunting back, also at our Coquitlam watershed, have brought us back to traditional meats. Growing our own vegetable gardens in community gardens also is a way we can sustain ourselves. Planting of native plants, herbs, medicinal plants, and teaching non-natives to get back to the land and the soil. Planting of fruit trees so we can freeze our fruit, picking of berries so we can continue to freeze the berries and make jams. My parents had a farm in Karamias. We were lucky, we grew our own vegetables with fruit trees, many fruit trees. On the farm, we had cows, sheep, lamb, mutton, chickens. We were able to have our own meats, own milk, eggs, make butter. Some of the old ways can still continue today, the smaller picture though. More community gardens would be beneficial to teach the youth and adults the joy of growing your own vegetables and fruits. I look forward to hearing Dr. Soo Kim's presentation and learn about 3D printing, which I really don't know much about other than I had dental imagery done, and I saw my jaw, which is a pretty nice looking jaw, on the screen, and I was really like shocked. Wow. So I'm really excited to hear what you have in store for us. For the bigger picture of agriculture, with global warming and climate change, increasing concentration of greenhouse gases into the atmosphere, floods, fires, we are all at risk, our planet Earth. Climate change can disrupt food availability, reduce access to foods, and affect food quality. Changes in our extreme weather events, reduction of water available can result in reduced agricultural productivity. Climate changes affect Indigenous people's food, affects all people's foods, impacts countries' food access, availability, diet, and nutrition. Examples: hunters choose lower quality, easy to capture, and abundant species over high quality, hard capture caribou can affect the nutrition of health of Indigenous communities. I'd like to say a quick prayer. Earth, teach me quiet. Earth, teach me humility. Earth, teach me caring as mothers nurture their young. Earth, teach me courage as the tree that stands alone. Earth, teach me freedom as the eagle that soars into the sky. Earth, teach me acceptance, renewal. Earth, teach me the ways to look after our lands, forests, waters, and sky. Earth, teach me to remember kindness always. Earth, teach me to walk in balance with the passing of each glorious sun. Haichka, thank you.
Okay. Well, thank you very, very much, Elder Marie, for starting us off in a good way. I really appreciate you joining us today and lift my hands up to you. We are so fortunate to be on this wonderful Burnaby campus on the unceded traditional territories of the Musqueam, Squamish, Tsleil-Waututh, and Coquitlam people. It's so interesting to think about our Indigenous ways of knowing and the ways we've harvested food for many years, and to learn from Indigenous people, but also to think about the other spectrum and obviously about the use of technology as well. And that's what we're going to hear about this evening. So we're here in person. Thank you for coming in person. It makes a big difference for our presenters to have an in-person audience, but also for those of you who are joining us online. We're going to hear from the amazing Dr. Soo Kim, who is going to share how he is empowering agriculture and food security through 3D printing. So I just want to tell you a little bit about the President's Faculty Lectures. This is a time-honored tradition here at SFU, and I want to really thank the team at Public Square. Thank you, thank you, thank you for doing such a great job of organizing it. And the idea is that we really showcase our amazing professors and the research that's happening here at Simon Fraser University. And this year, we're focused on a theme of making a difference for British Columbia. For those of you who don't know, this is one of the major foci of our new strategic plan at Simon Fraser University. And as a researcher myself, and now as a university president, I really do believe that university research can make a difference, and we are stepping up in so many ways to serve our province and our communities. And it's one of the things I love most about Simon Fraser University is the way that we do work with our communities together. And you're going to hear a little bit about that this evening. So this year we're holding our locations on a variety of these lectures on a variety of different locations in Surrey, downtown, and here on SFU Burnaby campus as well. And it's great to be here on Burnaby campus. So I just have a few housekeeping notes for this evening. So for those of you on Zoom, you can access captions for this event by pressing the CC button on the bottom of your screen. If you have any problems with that, you can send a message to hosts and panelists, and someone can help you out. We're gonna have a Q&A tonight, and I hope you all listen and think about questions that you'd like to ask. And we're going to use the ever popular Slido, and you can see the QR code here. Take a picture of it and connect with Slido. And I'm going to tell you that the 6-digit code for this evening for Slido is SFUPFL. SFUPFL. PFL. I don't know. Oh, President's Faculty Lecture. That's what it stands for. So you can submit your questions any point during the evening. I get to pose the questions, and so vote them up, ask questions. It really makes it a lot more meaningful if we can have that interaction. We also have community guidelines about how we engage in discussions with each other. And I encourage you to know about those guidelines and to utilize them. And there's a slide here that really overviews those for all of us. So now I get to introduce our amazing speaker for this evening. It's a long introduction, but you can slowly make your way up here. Dr. Soo Kim, professor in the School of Mechatronic Systems Engineering at Simon Fraser University. And he's been with us since 2010. And he serves as the scientific director of the BC Centre for Agritech Innovation. So before joining SFU, he was a senior research scientist at the Xerox Research Center for 2 years, and he spent time as a postdoctoral associate at MIT. I didn't know that. Very impressive. He earned his BS, his Bachelor's of Science degree at Yonsei University and completed his MSc and PhD at KAIST in South Korea, a wonderful institution that I have had the pleasure of visiting. He received the Quadrant Award in 2007 and the Hanwha Corporation's New Faculty Award in 2016. He's been an editorial board member for journals, including the IEEE Transactions on Electronic Devices, the IEEE Flexible Electronics, and the IOP Flexible and Printed Electronics and Advanced Sensor Research. I have no idea what any of that means, but it sounds very impressive to me. He's actively engaged in agricultural networks, serving on the steering committee of the BC Agricultural Climate Adaptation Research Network. And he's a member of Surrey's Agriculture and Food Policy Advisory Committee. So we're really very fortunate to have Soo as a member of our faculty and leading the Agritech Innovation Center here at Simon Fraser University. And so with no further ado, please put your hands together for Professor Soo Kim. You want the springer?
Thank you, President Johnson, for having me here today. And thank you, Elda Marie, for inspiring talk too. So, and also really thank all the audiences today. I can see some of my colleagues, friends, and all those mechatronics students too. So thank you for coming. And all of you in online, thank you so much for participating today's talk. So I would like to introduce you two different domains of technology, right? So people can think agriculture and one of the manufacturing technology, 3D printing. How can we, right, make a synergy, or how can we make a harmony? That's not easy thing. So today's introduction of technology for the agriculture is not going to be kind of exclusive to 3D printing. I want to make because my expertise is 3D printing. I want to make an example, but together with a combination of different cutting edge technologies. So today's overview, right? So we can talk about a lot of things today, but I want to give you one story, right? One story, how by the way, I'm the engineer, as introduced by President Johnson, right? So engineer, usually we call the problem solver or solution seeker. So in terms of my research area, my focus was two folders. One is biomedical application, another is environment and agriculture. So after becoming the BC Center for Agritech Innovations scientific director, my research moving toward more on the agri-tech side. So we can discuss that today a lot. So we're gonna start with thinking about recent climate change and climate crisis. And I wanna introduce you one of the important agri-tech or the agriculture sector we call the precision agriculture. Again, the reason I'm telling you why I'm the engineer, I'm trusting data, and the data tells everything to us nowadays. And then one of the spotlighted precision agriculture is basically data-driven agriculture methodology. We know farmers, right, make a decision based on their experience, like 10 years, 20 years of their experience. We move that kind of, right, practice of agriculture toward to the data-driven thing. That's basically precision agriculture. I'm going to introduce you to that, and then that domain can embrace the technologies like AI, robotics, and 3D printing, etc. And then I want to change a little bit of gear toward to 3D printing. I want to explain you because there are a lot of different knowledge on 3D printing in the audience, right? So I'm going to introduce you about the 3D printing, especially 3D printed systems we're working on in my research lab. And then eventually we will think together, how can we make a difference in BC by utilizing these technologies, right? So start with this. I think you saw this kind of carbon emission, global carbon emission, right? The charts a lot. Carbon emission, right, are on the rise really. So the big thing nowadays, because of this greenhouse gas effect and then climate change, right? So majority of governments target the net zero emission 2050, including Canada too, right? So how can you bend this curve? That's really important. This can cause a lot of damage and sacrifice for us. So, but if we can make any action or the bend the curve, then what's going to happen? This is the model by NASA in US, specifically in USA, specifically for North American soil, how soil can be dried up. So 2019, 2020, you can see even California, Texas area already somewhat close to desert. But what's going to happen in about 50 years or 100 years? They can become complete desert. And then BC and even close to, right, the US borderline, we're becoming close to current California or Texas. So this is a significant, really dramatic. So we need to do action now, right? Climate change is not the theoretical error, real threat to us, right? What about climate change in British Columbia? We know this, right? Already we saw a lot of big changes recent years. Like I just brought two examples, right? We know all the wildfire issue. It came earlier because of dryness, little rain, right? And also the flood in Abbotsford. So there are a lot of stress, specifically in agriculture area, right? The multiple stressors in soil health, right? So it basically reduces productivity and the competitiveness of Canadian farmers. And this is the model, Canadian model, right? So specifically compare two things. On your right side is April, springtime. On your left side is August, late summer. What's going to happen? So in the middle, you can see the delta P, which is precipitation change, right? Compare future and past. The future, they pick the 2050 to 2080, and then past the 20th century to 2005. You can see in spring, a lot positive, which means much more precipitation happening. This is modeled, right? And then in late summer, we can see negative things a lot in BC area, which means it's drier in summer than before. This is comparison between past and future. This tells really many things to us, right? So too much water in spring, which means during the seeding season, and then too little water during the growing season. That impact a lot in agriculture, right? So this kind of climate change we have in BC and Canada. So there are many aspects of efforts so far, but this is kind of summary, the introduction to you about what's going to happen nowadays globally and BC crisis in agriculture and food. Management and resource, water as a representative is really important, as you can see. And labor issues, I mean, gradually harder places, dangerous places, labor issue happen, and then robotics can be replaced. That's one solution for us. And then energy control and management is another thing we need to be careful about it, right? So those are the items we can discuss today. And eventually we can get food safety and security by controlling and managing this well. So I'm gonna bring you two different settings of examples. One, urban setting, food in terms of food security, and another thing is a farmland setting. So first one is urban setting. So there's a terminology we call the food desert. I don't know if you heard about it. Because of limited access of fresh food, nutritious food, in urban setting, I mean, low income area and etc., they can just access fast food, not fresh food, something like that. That's why they call the food desert, right? So this kind of happen really nowadays. And there are studies a lot in US because there are a lot of urban setting there, Canada too, right? So in Canadian cities, representatively Toronto, Vancouver, Montreal, those are studied. And this is Vancouver example. And you can see there's some warning colors, right? The orange color and red colors, even in Vancouver too, right? So these are food insecurity situation in urban setting. What about the farmland setting? I'm privileged actually to have a chance to visit, right, as a scientific director of BC Center for Agri-Tech Innovation, some farmlands. One of the, I took two examples. One example came from John Vulcan Academy Farm located in Langley. You see now water buffalo, right? So they grow water buffalo in order to get nutritious milk, right? And the interesting thing or very good thing is they grow their own grass organically by using vertical farming inside. And then you can think about it. If we have organic, right, the feeding to cow, and cow is healthy, and then milk can be healthy too, right? So this is one of the food security I observed. And another the observation I saw visited near Terrace, BC, up north there. There's a very innovative indigenous community. One of the innovative indigenous communities there, the named Tea Creek Farm. The leader is fantastic. We went there for the drone technology and the drone training program there, but they have their own food sovereignty. They grow everything, and then this is my lunch there, right? So everything grown, 100% grown by them. So they secure the food, and food sovereignty is there. So that's my observation, right? So coming back to, we have some terminologies today, so please understand. One real lesson I got from the interacting with indigenous community is regenerative agriculture. Nowadays, Canadian government and Canadian research, we are pushing this really a lot. And also it is related to soil health, basically. So we focus on the restoring and enhancing soil health and biodiversity. Basically, we always talk about diversity in human being, right? Same thing, right? So plant and crops, we need to secure biodiversity by having more carbon inside of soil. Carbon is very important for preserving water, etc. So aims to sequester, store carbon, improve water retention, and promote sustainable farming practices. So this is because of a copyright issue, I couldn't bring the film here, but I would like to encourage to see Kiss the Ground series in your YouTube, right? That's a beautiful series to encourage and promote the regenerative agriculture methodology. And basically, idea is, as you can imagine, carbon can be stored inside of soil. You can imagine, right? So can you imagine Earth atmosphere? What is the amount of carbon inside of Earth atmosphere? Which is?
40 parts per million?
Oh, good guess. So 750 billion tons, roughly. 750 billion tons. Guess how much of the carbon inside of soil? It's going to be more or less? Yes. So by prediction from the scientist, it is twice more. Twice more. So that's the way to go, actually, to cultivate and then diversify our soil, right? So biodiversity basically helps plants and animals to adapt to climate change. That's the key thing. So there's an effort, a lot of efforts from government sector, all the private sectors. You can see this triangle, right? So first, we want farmers practice new regenerative practice, which means soil can be more diversified, more carbon can be stored inside. There's a way in indigenous community, traditionally, they utilize, they call the cover crop, which means it's not the cash plant. Remaining area, they want to plant other crops in order to make the land utilized during the winter time too. So this kind of cover crop methodology, or they do like forestry together with agriculture. We call the agroforestry. So combination of forestry together with agriculture. This kind of traditional methodology can give us the lesson about this regenerative agriculture. And if farmers use this kind of new regenerative practice, scientists or engineers, our duty, right? Our role is sensing data collection to measure, predict these carbon inside of soil, right? By doing this practice, there's a third entity, which can be the government or the private companies, can make a predict model to give the credit to farmers, right? For example, at the moment, we don't have this kind of carbon credit, or we call the carbon offset program in Canada. But one of the examples is Japan. Japan is actually practicing this carbon offset program by government. So if farmer use biochar, they pay to farmer $20 per 1 ton of carbon, something like that. So I think many government needs to adopt this. So one of the private sector unicorn company in USA called Indigo. Indigo is not a book company there though. So Indigo is actually middleman. They gather carbon credit from the commodity producers like Apple or Amazon or Walmart or big companies, getting the credit and then giving back to farmer if farmer do this regenerative practice. So they very similar, like $17 per 1 ton of carbon, something like that. So these practices nowadays very good, I think, giving the incentive to farmers in order to practice, right, regenerative agriculture. So again, I want to emphasize as a scientist and the engineers, this is our role, sensing data. How can we sense and detect the soil carbon or soil, right, the health? That's the one I want to discuss today. So precision agriculture, I want to emphasize once again, we can save resources by sharply limit water, fertilizer, space. And then we can make a controlled environment, right? And then we can make a precise light control, temperature control, or airflow, something like a greenhouse, right? This kind of controlled environment. And eventually we can get the efficiency in production. We can reduce waste, and year-round growing is possible, like vertical farming or urban farming too, right? So what is the methodology then in order to get the precision agriculture? I think you got the concept of precision agriculture now, right? So we can precisely manage and control the resources to get the efficiency of production. Data. That's basically data-driven agriculture. So we distribute remote sensors, for example, and then getting signals from them. We use drone to scan the field and getting the information from them. And then based on that data, we can use precise amount of resources, water, fertilizer, those kind. That's the precision agriculture, right? So sensors are key technology element in this domain. Okay, I talk too much about introduction, but let's change the gear to 3D printing now. So yeah, actually, I don't know how many of you, I mean, engineering students probably knows 3D printing much better than other colleagues, but this is the 3D printing. So let's guess together. What is this? Glue gun, yeah. Glue gun is actually how it works. Heat up, right? And then glue stick is melt, right? And then melt, and then we can stick something and then make something, right? So same thing. 3D printing is actually not different with this, but there's one more element, which is robot. Robot is holding this glue gun like we call the print head, and then by X, Y, Z coordination, we design print it continuously. Difference between glue gun and 3D printing is glue gun is just a manual, 3D printing is automatic manufacturing, right? And of course, the 3D printing elements and components, it's not like a simple like a glue gun. There's a lot of different technology in terms of different print head technology, motor technology, and then of course material technology there, right? Those kind of in combination. My research is actually combining these guys to make some useful device, which is conductive, electrically conductive, and then showing some performance, mechanical or electrical, right? So another kind of general introduction of 3D printing, we call 3D printing as an additive process. There's two different things you can imagine. So conventional manufacturing, how do you manufacture something? We need to cut down. So we have, for example, metal ore, we need to cut to shape something. That we call the destructive way, right? But 3D printing is from the bottom, we build up something additively. That's why sometimes buzzword like additive manufacturing, I think you heard about that, right? So that's a 3D printing. So these two the simple video is showing you how 3D printing is actually working. So my grad students, wants to see very details of this layer. We call the layer by layer stacking. You can see that the one is we call the gyroid architecture. The other is octet architecture. So those are the kind of periodic truss structure, three-dimensional porous structure. So you can see gradual, right, growing up from the bottom, curvature like this, right? Or straight lines, something like this, building up from the bottom to top, right? This is a 3D printing actually. All right, so what are the advantages? I can bring up three advantages of 3D printing. One is design aspect, right? So initial, your target product to make seems like this, but it looks like some handle or something, but if you want to make mechanically durable and using less material by having optimized designing, then you can get this kind of different iteration of design. It's possible, right? And then eventually this can be printed. What is the difference between these and this? Design complexity is increased, right? If conventional manufacturing, like machining, this can be possible. But the conventional manufacturing may not be possible to make these sometimes, which means complexity is increased and manufacturing, there's some limitation. This chart gives you the idea, right? So if part complexity is increased, the unit manufacturing cost of conventional, traditional processes increased. But 3D printing, because it's building up the component from the bottom gradually, whatever complexity it has, it's possible to make. So that's the big difference between 3D printing and traditional manufacturing methodology. Another thing is, I really proud to say always this, 3D printing can be a democratized methodology. I mean, engineers sometimes hold their own technology and they are specialists, right? But the 3D printing is one field we can democratize technology somewhat. So conventional, consumer can buy products like this way, right? So production needs to be separate and then transport happen, shopping, and then eventually get your product. But think about if you can do 3D print by yourself or it near by you in your neighborhood, what's going to happen, right? Production and consumption can be very short cycle. We can make it easily. So this can be the benefit of the 3D printing. So we call that as a democratized technology. And also another factor there is we can make very sustainable way. There's the terminology we call the circular manufacturing. So compare with linear manufacturing like this, right? Linear manufacturing, circular manufacturing or circular economy can be, right, obtained in 3D printing because we can utilize material again and again and again, right, by 3D printing. So this is one aspect of sustainability in 3D printing technology. So these are somewhat introduction I want to introduce about 3D printing. Now, this is my lab. My research lab in Surrey, in SFU mechatronics department. So my lab very dedicated to two technology sets. One is architecture design. We really like to make a novel design of 3D shape, especially some, I'm gonna show you later about the origami, kirigami, those paper art inspired structures. And also we are very specialized in conductive 3D printing. So generally speaking, you can think about 3D printing is making just a prototype or shapes, but it's not. We actually want to make a finally usable, right, and the usable products by making electronics by 3D printing. So by utilizing these two specialties, architecture design and 3D conductive printing, we build a lot of interesting electronic devices, especially sensors. That's why my field moving toward to the agriculture because we have our own specialty in sensor technology. Yeah, so this is one of the examples. We have the robot arm in my lab. So you can see in the middle with some, what is this structure? Double helix. Good, right? So double helix can have very flexible motion possible, right? So we designed this as a kind of pressure sensor for building. And then in order to be the conductive sensor, one of the important things is conductive path trace must be followed this curvature. But use your 3D printer, desktop 3D printer, not available to make conductive line like that. But because we have a human arm, right? Similar human arm, similar, we call this a multi-axis robot arm. By using this, we can make a curvature and then trace printing is possible like this. So one robot build plastic structure and another robot can build this kind of a conductive path along this double helix structure. So this kind of capability we have. And also by utilizing that multi-directional 3D printing, we can make it, this is cube structured, we call the 3D, right? Structured electronics. We embed each individual components like inductor, capacitor, resistor inside of this. And then eventually interconnection can be finalized by this robot, right? So, sorry, robot head is too big in the first hand. But looking like this to finalize decoration of conductive material in order to make an interconnection, conductive interconnection, right? And also, this kind of robot, we are very interested. I'm gonna introduce you a few examples of robot hand. For example, for the application of fruit picking, right? We need to have some pressure sensible robot hand, we call the AND effector, right? Something like that. In order to make those, we need interconnection, which all the conductive line is really embedded or on the surface. So if we have this kind of valley structure and then want to make interconnection inside a component like that, use your 3D printer cannot build that. But our robot arm can move, swing like this to build this kind of conductor very well. So very precisely like that. Sorry, you cannot see much these small things, but yeah. All right, so let's move on then. These are 3D printing and the technology and the 3D printed systems we were working on in SFU, sorry, mechatronics lab. There will be some examples. I'm going to show you maybe 6 different examples what kind of devices are there to be applicable for agriculture or precision agriculture. One of the example people think about nowadays by printed electronics, printed sensor is disposable sensor. So by the substrate can be wood material, and then electrode conductive material can be decomposed by soil's microbial activity. So original conductivity can be gradually degraded, and then you can see how much microbial activity inside of soil is there, right? So this kind of sensor is one of the examples. So my lab, again, we are focusing on 3D printed sensors, but 2 tracks. One is biomedical application, and now agricultural application. So we've been doing a lot interesting steps to make the robot sensors for human and the robot interaction. So still several my PhD students and grad students working on that. But today's talk is agriculture. So let's just see, this is actually electrocardiogram measured by this robot, right? So we make a robot sensor, but that's not different with agriculture sensor actually. Subject change from human being to plant. So you can think about robot is sensing, detecting electrophysiology of plant or crops or fruits. You can think about it, but you can also think maybe efficiency is not that great because we have organs to show real signals strongly. We have hearts, electrical signals are very high, so we can detect easily. But fruits and crops, very minimal. You can think about it. So there's a signal intensity is quite low when we do same methodology to plant. Signal to noise, basically noise level is so high, right? And also another thing is productivity. I mean, one individual human being is precious. We need to put our wearables to individuals, but every fruits, can we do this, right? It's not. So productivity-wise, we need to think a strategy too. So in my lab, basically this is an overview of the agriculture and agri-tech strategy. We are working on data from that, the plant wearable, as I showed you in the previous page, and then image from drone and robot, right? This is important. So by utilizing that, we would like to make compare with the real setting, we can do the digital twin on them. And artificial intelligence, AI, is very important here, a very important player, because sensor data can be a lot, but we need to do classification. We need to prediction, those kind of things. Machine learning and AI is a big contribution to 3D printing technology, actually. And of course, big data is very important. Without big data, we can't make AI or machine learning. All right, so again, from here, I'm going to give you the examples, 5, 6 examples, practical examples, what kind of sensors we are working on with the 3D printed sensors, right? So number 1 is, again, 3D printed electrode for plant electrophysiology. This is the same methodology like a human's electrical physiology, right? But as I mentioned, we can measure every details of plant or crops, right? So we need to have some representative and then classification on them. That's important. My lab is focused on not the manual detection like this, but by utilizing the robot to have this kind of micro needle, and then holding that needle by robot arm, and then poke the leaf, and then getting the electrophysiology by itself. And then these robot can be kind of moving platform. So this is just my lab setting, but it must be moving around inside of greenhouse or field to detect very precise, right, the frequency and the location, etc. So getting this kind of signal is very important, because this sensor can give us plant electrophysiology data, can give us plant state. For example, if the insect comes to the plant, not easy to see visually, but if this kind of electrophysiology data can show us, right? So that is one thing we can see. And then again, these sensing data cannot play alone. It must be combined with AI and machine learning based classification. So this is not our research, but this is an example, right? So having this kind of plant wearables, and then that can give the real-time data collection to get the classification, and eventually healthy area or unhealthy area can be detected by prediction, right? So this is pretty nice. So we can move on this direction. Oops, maybe I clicked wrong thing. Yeah. Second thing, sorry. Second thing is about the 3D printed soil sensor. So 2019 was very interesting year for us, right before pandemic. 4 of my PhD students individual build up their own platform of sensors by 3D printing. I can show you those. So first one was, I'm not going to go very detailed on that, but this is a thin film transistor-based ion sensor. As you can imagine, soil, I mean, farmers need to know NPK very well. What are the NPK? Phosphorus, potassium. Those combination can give farmers information of their soil very well. So we would like to build that NPK sensors really much. So first approach was this, and then we can see really precise, I mean, depending on the concentration of potassium, we can get output really well. And then the other platform, I mean, the first platform done by Chow, he went to University of Cambridge for the postdoc. And this one done by Sin, he's now the technology consultant in one of the accelerator in Vancouver. He made the 3D printed electrode, and then these electrode is actually change the surface science. So interaction with water or interaction with ions, then these ions physically move around on top of this 3D printed electrode, something like this. So electrical power generated this kind of motion is possible, and then eventually sensor position. So two different droplets can mix together and then going into sensor position. So this kind of platform was developed. And another one is more interesting. So Tail actually graduated 3 years ago, and then he went to Baylor University as an assistant professor last year. And he built RF-based, you can imagine RFID, right? All the books in library have RFID, right? So RFID is the function of identification. But if that ID, RFID, has some environmental change, then that signal can shift. That can give us the sensing signal. So in that, the mechanism, we made wireless ion sensor. So if we can make a difference of the concentration, then different with the other ion, very base, we can get the signal differently like that. So our idea was making sustainable device from wood material. So wood-based cellulose was basing material for the 3D printing material, and eventually we can dispose this electrode sensor, right? That was our idea. And the fourth one is actually Manpreet, now the CE department's lecturer after her PhD. The combination of Tail, we made some visual kind of sensing opportunity. So this is robot hand, and the robot hand can be motorized depending on the soil extracts concentration difference. For example, potassium was like 10 to the negative 2 mole. Then we programmed the motion a bit low, very spontaneous like that. But when we increase the potassium concentration, then visibly we can see motion, bigger motion, right? The programmed inside. So basically our idea was environmental sensing or soil sensing can be seen visually, then we can see the quantitative value, something like that, right? So that was our idea. And another device I want to say is about by utilizing that RFID idea to RF sensor, 3D printed wireless fruit quality monitoring. So there are a bunch of different non-destructive detection of fruit matureness. People are working on that a lot. We have an idea like this. So somewhat precious fruit case like a kiwi, right? We can put RFID, and then we can get depending on matureness or ruinedness, we can get different signals or something like that. So our idea is making, interesting thing is that this electronic device is 3D printed, right? So all these bridges are 3D printed, etc. And we want to go that the wireless, the fruit quality detection process. Yeah. And another example, so probably going on a few more. So 3D printed and effector, as I mentioned, for harvesting, for labor issue, right? A lot of robot people or the mechanics people nowadays dedicated this research a lot in order to make really efficient robot hand to grasp and pick. One of the important things there is this hand needs to sense how stiff fruit is sometimes, right? And then how much force we can control to make a fragile, right, the fruit without any harm. That's most important thing. That's not easy task. Anyway, so people put a lot of efforts together to make a data transition even, and then suction cup, and then silicone skin and the pressure sensors, something like that. Very combination of technology there. So our research is dedicated to, again, lighter fingers, lighter robot hand formation by using the 3D printed truss structure. And then at the end of truss structure, we want to put the pressure sensor or force sensor or even electrical sensor. Then you can see some smart motion here. So if we have conductive, human touch, the insulator touch like that, with a minimal signal change, then the finger is not moving. But with a human touch, with a high signal change, then the motion is like that. So we want to build this kind of robot finger by 3D printing. that's one aspect. And by extending this discussion a little bit, we are very interested, again, architecture sensors. Oops, keep doing this, I'm sorry. So we are very interested in, we call the architecture design, like origami, kirigami. Those are the Japanese paper, right? Art-based one. So origami is in Japanese, the meaning is folding, bending, and kirigami is cutting. By doing those, we can build something, right? So something like this tube was one of the example we build, and then this tube can be miniaturized, right? And then eventually that tube can give us the pressure information. So I'm not going to go the mechanisms. I'm sorry. Oops. Yeah. So when we grasp some object, right, that the pressure sensor can, right, sense that force, then the electrical conductivity, sorry, the resistivity reduction significantly, which means conduction happen, and then we sense how much force is applied, something like that. So this kind of end effector we are working on. And by doing this gripper sensor to actuator, so you can think about this way, the robot arm needs to be controlled by some brain eventually, like our brain, right? But what about without brain? Is there any kind of non-conscious actuation possible? That's our idea to start with. So there's a device called synaptic transistor that shows a non-volatile effect. Non-volatile means the signal is not volatile, it remains inside. So when we call it training, but when we touch ball a few times by giving this input, the signal is accumulated without volatile behavior. That means initially we have a small force to, the slipping the ball with that force. But because of this training, 1, 2, 3 times training, signal can be accumulated. So even with the small original signal, we can eventually hold the ball. So that's our sensing to actuation, the mechanism. So this is recently we published, and then this can be applicable to the end effector eventually. That's our aim. All right, so 2 more. So one interesting thing nowadays we are very interested in the greenhouse setting is the farmers would like to see the wind sensing, how strong wind is actually blowing in order to control their airflow and etc. So people done, this is not our work, people done a lot with, they call the triboelectric sensor. So by using that triboelectric material, then they can sense, right, certain wind, and then if it is strong enough, they can give the warning sign to or the farmers or something like that. Can we make simple wind sensor by 3D printing? That's our aim to do. So eventually this is done by kirigami. So this structure is a kirigami structure, and then you can see very small vibration here, right? So this vibration can be detected even you're walking. As strong wind sensing is not a big deal. So we apply this to the, wind sensing and the vibration sensing, stuff like that nowadays. Last but not least, so that's a recent development in my lab. So we call 3D printed drone. So who can imagine drone can be 3D printed, because structure can be fragile sometimes, 3D printing, right? But nowadays we can make really reinforced, right, material and structure that can have that architecture design of the body and frame of 3D printing. So that's why we call DIY 3D printed drone. DIY is a do it yourself, right? So we instead of having commercial drone, we want to build our own drone to scan the field. The eventual goal we need to do. Oh, by the way, this is the flying drone we built.
Pretty good.
Right?
Can you lower it a little bit?
Yeah. So this is the example. So we can improve agriculture workflow with a sustainable practice. This is a scan image, red spots you can see with weeds. Then after this scanning, drone can spray only those spots. In other words, we can reduce the use of pesticides, targeted spray, right? This is the precision agriculture. So sensor is one part, important part. The other part is by visual sensing like this, by drone, we can have the precision agriculture strategy, right? Yeah. All right. So I think almost done. So this shows you the idea, what is the future direction then? I show you several examples of 3D printed devices, 3D printed robot arms, 3D printed robot sensor, etc. Right? So we need to combine technology to move forward. As I said, sensor technology, mechatronics, robotics, plant electrophysiology, manufacturing, 3D printing, right? And data management, big data, eventually AI, algorithm setting. So a lot to do. So my team, actually not just one single domain of the discipline, we have really interdisciplinary team. So this is important in agriculture sector, I believe. So connecting engineering concepts, technology, and partnership. This is, I think, a message I want to give you. So I'm not promoting this book, but the book name is Nature of Technology. This author says, technological evolution is actually combinator evolution. One kind of genius develop and invent something? No, we build up knowledge as a collective efforts, right? And then combining existing technologies together. So we can make innovation happen from this kind of technology intersection. So by utilizing 3D printed architecture design, we have a conductive printing specialty to put the 3D printed Internet of Things or sensor, and then eventually smart farming innovation is possible. Okay, so I want to thank my students, previous students, and the current students and collaborators, and my dear colleagues in BC Center for Agri-Tech Innovation, and full support from the funding agencies. Thank you for your attention.
So now that was fantastic, Soo. Thank you ever so much. I'm going to just remind all of you about Slido. You can put questions in Slido, and I think there's, I don't know, and yeah, there is the QR code there. Fantastic. And I will look at them in a minute, but I have a million questions. Okay, there were certain things I did not understand. I want to tell you that right now, but I was really fascinated by your presentation. So maybe first of all, how far away are we from moving these technologies into practical applications?
Exactly. So I brought up mainly 3D printing platform technology today, but it is not alone, as I said. Powerful kind of progress can be made together with like artificial intelligence, machine learning, big data, etc. So the reason I'm telling that is already AI and machine learning is in place in greenhouse, for example, autonomous greenhouse strategy. They're using AI a lot in the field. I think 3D printed devices and customization by 3D printing is not far away too.
Okay, fascinating. And so, you know, even working with the Agri-Tech Innovation Center and farmers who are, you know, developing crops, doing their work, is there resistance to thinking about these new technologies, or are they really adopting these new technologies?
Exactly. So any fields, new technology comes in, then there's some resist. I mean, I think that's natural. And especially for 3D printing or some high cutting edge technologies, they need some resources in terms of machine cost is sometimes high, and service cost is high. For example, drone scanning, they need a software to analyze data. It costs subscription based, cost a lot, right? So I think there's some resistance, but whenever they are open-minded to the cutting-edge technologies, there's a solution.
Okay,
Yeah.
interesting. Yeah, so part of the work is just to also work with them to see the possibilities, I
Right,
imagine,
right.
as well. So the other thing I was wondering about, so in your lab, you've got these wonderful arms. You gave this great demonstration of the helix, et cetera.
Right.
So can this be scaled up then? So that you could print, like, is that the next thing that has to be thought through, is how to scale it?
Very
or-
good question. So, I mean, when it comes to 3D printing, we can compare comparable to mass production.
Okay,
So our aim is getting very niche and customizable thing. So if we demonstrate some certain possibility of devices by 3D printing, mass production can be different story. So
Okay.
yeah.
so is that a big leap to move to mass production then?
Mhm.
Yes. And would that be something you'd also be looking at in the future, trying to think through that problem?
Exactly.
Yeah.
Exactly.
Fascinating. You know, you touched on this, and we held Elder Marie started us off by talking about Indigenous ways of knowing. I'm really interested in your interaction with the Indigenous community. It was
Tea Creek Farm.
Tea Creek Farm.
I
So are
think-
they using traditional techniques
Exactly.
as well, or?
Absolutely.
So
So-
tell me about that kind of combination of things.
Thank you, Jody. So one of the fascinating thing to me was indigenous communities are very open-minded.
Yeah.
We approach them with some culture sensitivity and respect. Actually, that's very important when we approach an indigenous community. But recently, I realized they are very open-minded for high tech or cutting-edge technologies. They have a mindset to combine their traditional methodology together with high tech, right? So T-Creek is one of the example. We have a strong tie and interaction with BC Kai, but there are other First Nations we are working together in the coastal area and then Kelowna area. So we gradually broaden our kind of interaction together with all the First Nations in BC.
Yeah, that's fascinating, because you don't often think about that kind of combination, right? Of traditional ways of knowing and then also this new technologies. That's
Exactly.
fantastic. It's great. Okay, there are questions that are coming in. Thank you, everyone. I see you putting your questions up on the Slido, so I'm going to ask you a few of these as well. How are you planning to translate? This is kind of related to the question I asked, but maybe a bit more detail. How are you planning to translate the knowledge, ground truth by generations of farmers into data-driven insights? How do you take that forward?
I see. That's a very good question. So that, I mean, that doesn't mean data-driven agriculture doesn't mean disregarding farmers' experience. So we need to, again, nowadays I'm really interested in making harmonization or synergy between two sides. As I explained to you about traditional indigenous communities methodology together with cutting edge technology, between big farms and small farms, between university and practical industry. This is the same thing. For the farmers' experience is very important. Even though we rely on data, we can reinforce their experience together with precision agriculture, I believe.
Oh, that's fascinating. I'm also wondering, another question that's come up is, can you describe how BC farmers and food producers and agri-tech companies can benefit by working more closely with university researchers? So maybe a little bit about the BC Kai model, and then how to bring these, I mean, it's really interesting to think about how we can bring these different groups together.
Exactly. I think we need to build the ecosystem together. So we need to respect each individual stakeholder, right? So university, historically silo, right? Somehow they do their research sometimes. I'm doing my research too, but we need to hear a lot from other stakeholders. So we better bring all these stakeholders on this common ground. That's the important thing. So BC Center for Agri-Tech Innovation, I'm promoting, is doing that job actually. We would like to bring stakeholders very frequently meet each other to create the idea together and then circulate the future directions together, stuff like that.
Oh, that's fantastic. That's great. You know, someone in the has asked the question about how can people who are interested in this, and I know there are some people from, you know, the farming system watching online today. How can people keep up to date with what you're working on and kind of try to start to think about, you know, applications or engagement, et cetera? Are you sharing these innovations with a broader community?
Broader community, yeah, by publication.
Yeah, or, you know, just by, you know, I just don't know, you know, how you, in particular, mobilize the knowledge with the farming community, help them see what the possibilities might be.
That's a good question. So basically, it's the same discussion with ecosystem building. We would like to touch base with farmers and growers and farming companies and greenhouse companies very frequently to introduce not just our technology, but the cutting edge, the agri-tech technology frequently, right? Through, for example, communication is one big element in BCKI's activity. So we want to promote technology, promote the others' work very frequently. Yeah.
And does BCKI, are you sharing the results of your work on a website, or can people follow it, or is that something to come in the future? Or?
Exactly. So BCKI has our own website, and then promoting success story of our projects.
Yeah.
For example, we just started about a year ago, so we don't have many success story yet, but we have a fruitful results of that combination or kind of projects together with the companies and the universities, etc. So we share that in the website and then newsletters, etc.
Oh, that's great, because I think there's going to be growing interest in this as well.
Exactly.
I think the other thing that people might not realize is that BCKI got started, and this whole through an investment of our provincial government, because they also are very interested in this food security question.
Exactly.
And making sure that that the population of British Columbia will have food to access into the future.
Exactly.
Yeah.
We are very, how can I say, privileged and proud of working this field at the moment, because this is real interest to serve our BC, right? The residents and the Canadians at the moment.
Yeah. There's a question online as well, Wusu, about you traveling to other countries and that are leading in agri-tech, like the Netherlands, and what we can do to support and scale the most effective uses of technology. So, you know, what are you learning from the Netherlands, from other places, in terms of thinking about what we need to do here in British Columbia to keep moving forward?
Right. That's a good question. So again, I was privileged to visit Netherlands on the summer as a scientific director together with my colleagues in BCKI, and we observed their advancement in horticulture and the agriculture area. And of course, individual country has different priority and crops are different, etc. But we realized, although their target and our target is slightly different, core technology underneath is similar. Drone technology, sensor technology, right? So we share the knowledge together and then build up the collaboration nowadays with the Netherlands.
Yeah, it's interesting. I know that that Wageningen University came, and we have a MOU with Wageningen. And Wageningen is the world leader in agricultural science right now.
Right.
But they came to SFU.
Exactly.
Because they want to work with us. And so what do they see in what we have to offer? Do you have a sense of that?
Yeah, thank you. They saw real potential in BC. As you know, BC agriculture land is humongous, and a lot of I think they see BC as an emerging market. So Wageningen University, they didn't come alone. They brought Netherlands company together, and in order, match with all the BC companies. So that was very good opportunity to us to engage with the Netherlands in that way.
Yeah, no, it was fantastic. I think they also saw, and you raised this, the capacity that we have at SFU around the AI space as well, and the computational areas, an area that we have a lot of strength in that they didn't have as much strength in. So it's a nice little match as well in terms of that. Okay, here's a real science question for you. Did the NPK sensors face corrosion problems over time? I think that might be from one of your students in the room.
Maybe someone who has an engineering background. Yes.
Tell me again, what's an NPK? Oh, this is the phosphate.
Nitrogen, phosphorus,
All
and
right,
the
got it.
potassium.
Okay,
So those are
they're sitting in the soil.
sitting in the soil,
Right.
the nutrient,
Yeah.
right? So soil nutrient farmer, individual kind of cherry grower or apple grower, ratio of NPK can be slightly different.
Okay.
So they want to know their source NPK ratio, something like that, in order to keep making their fruit productivity, right? So NPK sensor we develop actually, that's true. So there's some corrosion problem because of material limitation. We would like to improve that. So I don't know who asked that, but maybe let's talk later details of that. Thank
Yeah,
you.
no, that's fantastic. And I guess, see, I haven't ever really thought about 3D printing, but you are printing with very, very different materials always, right?
Exactly.
And so you have to find the right materials
Right.
in order to deal with these kinds of problems.
Find the best material and then develop our own material. That's a important part.
And are you developing materials in your lab as well?
Yes.
Oh, that's fascinating.
I
Interesting.
mean, developing doesn't mean to create something, but it's again, combination of different material make a novel property.
Okay, that's fascinating, absolutely fascinating. Okay, here's another question for you that I wouldn't have known to ask. How far has AI and ML been implemented in agriculture? Has
Oh.
AI and ML been implemented in any of your projects or in other agricultural fields?
Yes, as I introduced you briefly, two aspects of machine learning play in my research. One is sensor data classification, and then the other one is algorithm building from the drone scanning, right? So this is very important. And also, as I said, these are already, right, in the field that people are using it, right? So in sensor technology, I mean, commercial sensor companies, they not share their own strategy much, but we know they are using classification a lot. And also, as I mentioned, in the greenhouses, I observed in the Netherlands visit, greenhouse growers would like to utilize autonomous, right, the climate control by using AI already. So there are companies, growing field of companies, they are using AI to implement in the greenhouse strategy. They are already right there. So, yeah.
That's really interesting. I'm going to come back to these questions, but another thing I was wondering about, Soo, is, I mean, you moved into this area because you saw the possibility, right? And it's interesting, you know, from medical devices into this area as well. What are we going to do to get other people excited about this area of agri-tech innovation and to really, I mean, there's a huge challenge for us in terms of our food supply. Are you enticing people into this area, or what can we be doing?
Oh, thanks, Joy. So basically, it's okay if you forget about 3D printing after leaving the door. But I want you to remember about the precision agriculture, data-driven agriculture, right? So I think that's a way to go, right? In order to manage and control the resources in climate change era, right? In the global boiling era, right? So we need to utilize our resources smartly. So people in agriculture field using this precision agriculture really a lot. And I think that's my passion. And the sensor is a critical element there. And my fundamental view, sensor technology is there in my lab, whether it is biomedical sensor or agriculture sensor. We're going to work on this sensor for a long time. So that's my passion.
Well, that's fantastic. Yeah, I think there's a lot of opportunity. And SFU is going to be offering a certificate program, I think, at some point in agricultural technology. Is that?
I mean, in order to train BC, how can I say, young generations?
Yeah.
Mechatronics engineering launch agri-tech concentration, actually.
Concentration.
Yeah.
Fantastic.
It's kind of an option. So students after undergrad degree, they can go to the field and then do their contribution to agri-tech, I believe. So I think for younger generation, I think this is very important. We need to change our mindset or perception that the agriculture and agri-tech, there's potential. Engineers can contribute to agriculture and agri-tech. Yeah.
That's fantastic. What did you say at the very beginning? Engineers are problem solvers and
Solution seeker.
solution seekers. I love
Yeah.
that. That's fantastic. So listen, everyone, we are drawing to the end of our time together. I know there are more questions and I see you still are posing them online, but I'm sure Soo, for those of you in the room, wouldn't mind taking a question or two if you want to hang out for a few minutes. So thank you. But I do want to really thank you for a really fascinating lecture. I think it really opened my eyes to the possibilities. I hope our audience as well get a sense of really what the opportunities are in this field. I'm really, going to be fascinated to see the next 10 years, and because we do have a challenge in front of us in terms of climate change and do need these solutions. So I'm really going to be interested to be following your work, your students' work, and seeing how we can progress in moving this technology forward. I want to thank everyone in the room tonight, those of you who've joined us online as well. And before you go, I have a few thank yous as well. I want to say thank you to the SFU IT team for helping us broadcast this evening from SFU's Applied Sciences building on the Burnaby campus. I want to thank our great team at Public Square. Thank you all. I want to thank Janet, Seth, Gabrielle, Savannah, Nola, Gabrielle, Sophia, Ina, as well as our wonderful volunteers. It does take a village to put something like this together. Deeply appreciate it. And it's great. It's great to bring people together to hear our amazing researchers and to answer these questions. So thank you. I hope you've enjoyed tonight's event. We are going to have another great President's Faculty Lecture on November 29th featuring Carolyn Colleen. It's going to be a very interesting area as well. I hope you can join us. But in the meantime, please put your hands together virtually and in the room and thank our amazing speakers. Thank you. That's great. Thank you so much. Thanks, everyone.